Have you ever found yourself just like frantically refreshing a web page, maybe tracking a package you really need, or watching a stock price update, just hoping for that instant change?
Oh yeah, that feeling of wanting information right now.
Exactly. That urge points directly to what we're exploring today. Imagine a world where information doesn't just get lumped together and processed, at the end of the day,
Right, not in big chunks.
but flows continuously, reacting instantly to every tiny change. Today, we're diving deep into the powerful world of stream processing.
And what's truly fascinating here, I think, is how fundamentally different this is from the traditional ways we've thought about data.
How so?
Well, instead of waiting for a complete finite data set to analyze, we're dealing with data that's unbounded. It just keeps arriving incrementally over time. It's a truly never-ending flow.
A never-ending flow. That's a crucial distinction. So when we talk about that, what are the immediate benefits compared to, the old way?
Speed is the big one, real-time reaction.
Right. So our mission in this deep dive is to explore how this continuous flow actually works, why it's so vital for those instant updates, and how it's fundamentally transforming the way we handle information in real time. We're going to be extracting the most important insights from our source material on this for you.
Sounds good.
So most of us are probably familiar with batch processing. Think of it like processing a huge pile of mail all at once, right, at the end of the day.
Yeah, the traditional method.
Traditionally, this approach assumes your input is bounded, meaning it's a known finite size. Like the sorting operation in systems like MapReduce, it actually has to read its entire input before it can even start producing output.
Which, well, that begs the question, what happens when data never ends?
Good point.
Like continuous user activity on a website or constant sensor readings or, the financial markets. The data set is never truly complete in a meaningful way.
Ah, I see.
And that's precisely where batch processing just hits a wall because changes might only get reflected maybe a day later.
A day later, wow.
Yeah. Which is simply too slow for many impatient users today. We expect things instantly now.
We really do. And this is where the magic happens. The solution, of course, is stream processing. It processes every event as it happens, immediately.
Right, event by event.
Our sources define a stream as data that's incrementally made available over time. And you see it everywhere, actually, from simple stint-stout pipes in Unix to TCP connections, even how audio and video get delivered over the internet.
It's pretty fundamental.
It is. And there's this wonderful quote from John Gall that kind of captures this evolution perfectly. He said, "A complex system that works is invariably found to have evolved from a simple system that works."
I like that.
The inverse proposition also appears to be true. A complex system designed from scratch never works and cannot be made to work. It just beautifully illustrates how we've gradually evolved from those simpler foundational batch systems to the immensely powerful, but more complex world of stream processing.
That makes sense. Stepping back for a moment, in stream processing, a record is typically known as an event. It's usually small, self-contained, immutable.
Immutable, okay.
Yeah, an immutable object with a timestamp, detailing something specific that happened, like a user viewing a page or a sensor taking a temperature measurement, or just a single line in a web server log file.
Little packets of information.
Exactly.
Yeah.
And these events are generated by a producer, sometimes called a publisher or sender, and then they're processed by consumers, also known as subscribers or recipients.
Okay.
Related events usually get grouped together into a topic or a stream. And this whole model is vastly more efficient than, say, constantly polling a traditional database for new info.
Right. Instead of asking anything new, anything new.
Yeah, exactly. Instead, consumers are just notified instantly when new events appear. Much better.
So we've got these individual events, these tiny bits of crucial information. How do they actually travel? From where they're born to where they need to be processed. What are the common pipes for this?
Well, our sources talk about two main pathways. First, there's direct messaging.
Direct messaging.
I think of it like a private chat channel. Systems like UDP Multicast, which is used a lot in finance for super low latency stock feeds, or brokerless libraries like ZeroMQ, they rely on direct network communication. Webhooks are another example, where one service notifies another directly, maybe via HTTP or RPC.
Sounds efficient. Are there downsides?
Oh yeah, definitely. These systems have inherent limitations. Your application code needs to be really aware of potential message loss. Fault tolerance is limited, and producers and consumers generally need to be constantly online.
So if a consumer goes offline,
Hmm.
they just miss critical messages entirely.
Pretty much, yeah. That sounds like a big problem for, say, a real-time order system or
It
something.
does. Is that where the message broker comes in
Mm.
to provide that reliability?
Precisely. When you need more robustness, you turn to a message broker. Think of it as a specialized database, really,
Yeah.
but optimized for message streams.
Okay, a database for messages.
Kind of. It usually runs as a central server, and producers and consumers connect to it as clients. Producers write messages to the broker, consumers receive them by reading from the broker. It centralizes the data flow,
And that makes it more robust.
much more tolerant to clients connecting, disconnecting, or, crashing.
Hmm.
Message durability is moved to the broker itself. Often you can configure it to write to disk.
Right.
And critically, if a consumer is slow, these brokers generally allow for unbounded queuing rather than just dropping messages or pushing back. So messages aren't lost.
That's key.
And another key point, consumers are generally asynchronous. A producer sends a message and typically waits only for the broker to confirm it's buffered, not for it to be fully processed by the end consumer.
Okay, so it's asynchronous then. That begs the question, though. How do these brokers differ from traditional databases? They sound kind of similar at a high level.
It's a great question because they really have distinct purposes. Traditional databases usually keep data until you explicitly delete it, right? Whereas most message brokers automatically delete a message once it's successfully delivered to its consumers. They aren't really designed for long-term data storage.
I see. Different jobs.
Exactly. Brokers also assume their queues are fairly short, whereas databases support complex queries, secondary indexes, all that stuff. You'll find traditional message brokers built on standards like JMS and AMQP, think RabbitMQ, ActiveMQ.
Okay. And what if you have multiple consumers reading the same thing?
Good question. Two main patterns there. Load balancing, where each message goes to one consumer in a group. That shares the processing work great for expensive operations.
Makes sense.
And fan out, where each message goes to all consumers, like having multiple different batch jobs all reading the same input data.
Got it. Now, you mentioned consumers can crash. What happens then?
Right, so brokers use acknowledgments. If a message isn't acknowledged, the broker assumes it wasn't processed, and it'll redeliver it maybe to another consumer if you're load balancing.
Ah, redelivery.
Yeah, and this redelivery, especially with load balancing, can lead to messages being reordered.
How so?
Well, imagine message M3 goes to consumer 2. Consumer 2 processes it, but crashes before acknowledging. Meanwhile, consumer 1 picks up the next message, M4. Then, the broker redelivers M3, maybe to consumer 1.
So consumer 1 sees M4 before M3.
Exactly. Even though M3 was sent earlier, so ordering isn't always guaranteed across redeliveries in that model.
Okay, so we've seen direct messaging fast but fragile, traditional brokers more robust, but maybe ordering issues and not for long-term storage. What's the next step? Is there a model that tries to bring the best of both worlds? Durability like a database, but real-time speed.
Absolutely. Our sources highlight a third, and I think incredibly powerful model. Yeah. Partitioned logs.
Partition logs.
Yeah, this truly combines the durable storage capabilities of databases with the low latency notifications you get from messaging systems.
How does that work? What exactly is a log in this context? Is it like a log file?
Sort of, yeah. A log at its core is simply an append-only sequence of records on disk. Producers send messages by just appending them to the very end of this log.
Just adding to the end?
Yep. And consumers receive messages by reading the log sequentially from wherever they last left off. If a consumer reads to the end, it just waits for a notification that a new message has been appended. It's very much like the Unix tail-f command, if you know that.
Okay, tail-f on a file. I get that. But how does that scale?
Right, so to scale it, the log gets partitioned, usually across different machines. Each partition acts as its own separate independent log. A topic then simply becomes a group of these partitions.
So a topic is multiple logs.
Essentially, yeah, a group of partitions. And within each partition, the broker assigns a monotonically increasing sequence number. They call it an offset to every message. That guarantees total ordering within that specific partition.
Ordering within the partition. Got it.
Yeah. And prominent examples you might have heard of are Apache Kafka, Amazon Kinesis Streams, and Twitter's distributed log.
Okay, Kafka is definitely one I've heard a lot about, so this is where it gets really interesting for me. How do these partitioned logs address the limitations we saw with traditional message brokers, like the message deletion and load balancing?
Right. Well, the fundamental difference is that reading a message from a log doesn't delete it.
Ah.
So that
Yeah.
trivially supports fan out because multiple consumers can read the same stream independently without messing things up for each other.
Makes sense. And load balancing.
For load balancing, instead of assigning individual messages, they assign entire partitions to consumer nodes.
Whole partitions, that's a key
It
difference.
is. Now, the downside of this sort of coarse-grained load balancing is that your maximum number of concurrent consumers is limited by the number of partitions you have for that topic.
Ah, okay.
And also, if a single message is slow to process within a partition, it holds up the processing of all subsequent messages in that same partition.
Because the order within the partition is strict.
Exactly. But they are ideal for really high throughput situations where individual messages are fast to process and where that message ordering within a partition is critical. For example, if you use, say, a user ID as your partitioning key, you guarantee that all events for that specific user are processed in the correct order by the same consumer.
That's powerful. Zooming out a bit, what are some of the other implications of this log-based approach? It sounds like it goes beyond just messaging.
It absolutely does. These consumer offsets, remember the sequence numbers? They're conceptually similar to replication logs in databases. They let consumers precisely track their progress. So if a consumer disconnects, it can just reconnect and pick up exactly where it left off without missing a single message.
Like a bookmark.
Pretty much. The broker acts like a leader database and the consumer like a follower.
Yeah.
And when it comes to disk space, because you're not deleting messages, log-based systems use something called log compaction.
Log compaction, what's that?
It's a clever technique. The storage engine periodically scans for records with the same key, discards the older duplicates, and just keeps the most recent update for each key.
So it keeps the latest value, but throws away the history for that key.
Exactly. This prevents the logs from growing indefinitely, while still effectively retaining a full historical view of the latest value for every key. It creates this sort of bounded size buffer on disk that can hold days or even weeks of messages at a constant throughput, regardless of how far behind a consumer might fall.
That seems like a huge operational advantage.
It is. If one consumer falls behind, only that consumer is affected, not the whole system. You can even hook up a development or debugging consumer to a production log without disrupting anything live.
Wow.
And maybe the most transformative feature is the ability to replay old messages. Since consuming is read-only and doesn't delete, you can easily just reset a consumer's offset to an earlier point and reprocess past messages.
So they can rerun history?
Effectively, yeah. It really blurs the line between stream and batch processing. It's incredibly powerful for reprocessing data with new code or recovering from errors by simply replaying what happened.
What's the takeaway here then? We've seen how streams work, but our sources highlight this really profound connection. The idea that writes to a database are themselves just events that can be captured and streamed.
Yeah, that's a mind bender. And it begs the question, in a complex application with multiple systems, say, your main OLTP database handling live transactions, maybe a cache, a search index, a data warehouse, how do you keep them all reliably in sync when data changes?
Good question. What are the usual ways?
Traditionally, you might use ETL processes, right? Taking a full batch copy of the database periodically. Or you might try dual writes.
Dual writes, meaning the application writes to both places.
Exactly. The application code explicitly writes to the database in the search index, for example. But dual writes have critical problems.
Like what?
Well, imagine this scenario our sources describe. Client 1 updates an item in the database, then tries to update the search index. But at the exact same time, Client 2 updates the same item.
Uh-oh. Race condition.
Classic race condition. If those operations get interleaved, maybe Client 2 updates the database before Client 1 manages to update the index, you can easily end up with the database and the search index showing completely different, inconsistent information. Permanently inconsistent.
Yikes.
And another issue is fault tolerance. What if one write succeeds but the other fails? Again, inconsistency. Trying to ensure both succeed or both fail atomically is a version of the atomic commit problem, which is notoriously difficult and expensive to solve in distributed systems.
Okay, so dual writes are risky. We need a way to ensure all these different systems stay consistent in real time without these race conditions or fault issues. What's the clever solution our sources present for this?
This is where change data capture, or CDC, becomes incredibly powerful.
Change data capture, CDC.
Yep. It's the process of observing all data changes made to a primary database and extracting them as a stream of events, immediately as they are written.
Interesting. So how does CDC ensure consistency across multiple systems then? It sounds like you're just capturing the changes after the fact.
Well, stepping back, CDC essentially makes one database the leader, the definitive source of truth from which all changes are captured. and it turns the other systems, like caches or search indexes, into followers.
Okay, leader follower.
By applying the changes captured from the leader in the exact same order as they happen in the source database, you can ensure eventual consistency across all the follower systems. It elegantly avoids that race condition problem we just talked about.
So the order is key. How do you implement CDC?
It can involve using database triggers, though those can sometimes be fragile and add overhead. A more robust approach, often used, is parsing the database's internal replication log, the same log used for database replication itself. Systems like LinkedIn Database or tools within the Kafka Connect framework do this.
Parsing the replication log, that clever.
Yeah. And CDC is usually asynchronous, meaning the source database doesn't wait for changes to be applied downstream,
Oh.
which is good operationally, but it does introduce that possibility of replication lag.
Right, the followers might be slightly behind. What about setting up a new follower, like a new search index?
Good point. You might need an initial snapshot of the source database first, and then start applying the changelog from that point onwards. However, our sources highlight something neat. Log compaction, like we discussed with Kafka, can help here too.
How?
By keeping only the most recent update for each key in the changelog itself, you can potentially rebuild a full, current copy of the database state just from the compacted changelog, without needing a separate, potentially locking full snapshot from the source database. That's a huge operational benefit.
That is neat. Let's dig into that idea a bit further, though. Closely related to CDC is event sourcing. It's a technique where the application's logic is explicitly built on immutable events from the start. Instead of a database just recording the current state, it records the sequence of actions that led to that state. What's the core difference here compared to CDC, and why choose one over the other?
Yeah, what's truly fascinating here is the difference in the level of abstraction. With CDC, the application mutates to the database in a conventional way, right? Update rows, delete rows. Then low-level changes captured from the database's internal logs, like rowx changed.
Okay.
With event sourcing, the application itself thinks in terms of and writes immutable application-level events. For example, an event might be student cancel enrollment, rather than just a low-level entry deleted from enrollments table.
So it's more domain-specific, more meaningful events.
Exactly, higher level. And this approach offers several compelling advantages. It can make it easier to evolve applications over time because the history is preserved. It greatly aids in debugging Ts. You have a clear, auditable history of exactly what happened and why.
Like an audit log built in.
Precisely. It can even guard against certain application bugs by making state changes explicit events. The current state in an event source system is always derived from this full event log by replaying the events.
Derived. So you calculate the state from the history.
Yep. And unlike some CDC scenarios where compaction might discard old versions, event sourcing generally requires the full history of events to reconstruct past states accurately. So log compaction in the same way often isn't suitable if you need that full history.
Got it.
It also cleanly distinguishes between a command, which is like a user request that might still fail validation, and an event, which represents an accepted command that is now a durable, immutable fact about the past.
Command versus event. Okay. So the upshot of all this, whether CDC or event sourcing, is that the core idea seems to be that mutable state, what you typically see in a database, and an append-only log of immutable events, the stream, are really two sides of the same coin.
Exactly. Pat Helland, who's quoted in our source, puts it really profoundly. The truth is the log. The database is a cache of a subset of the log.
The truth is the log.
Wow.
What are the big advantages of adopting this, like, log-centric perspective?
Well, it's not just a clever analogy. It fundamentally flips how we can think about data and build systems. Thinking of every change as an immutable event in a log unlocks massive benefits.
Such as?
Well, first, instant auditability. Just like a financial accounting ledger, it makes it far easier to recover from errors or diagnose exactly what happened when.
Yeah, that makes sense.
Immutable events also capture richer information. For instance, in an e-commerce scenario, you might know a customer considered an item, put it in their cart. Even if they later removed it, information lost in a traditional state-only database.
More context.
Right. Furthermore, by separating the mutable state, the derived view, from the immutable event log, the truth, you can easily derive multiple different read-oriented views from the same event log. This makes it easier to support new features or different query needs without impacting the core write path.
That sounds like CQRS, command query responsibility segregation.
Exactly. It fits very well with CQRS patterns, separating how you handle commands, writes to the log, from how you handle queries. reading derived views.
Are there downsides to this log-centric view?
Well, the asynchronous nature of consumers means you can get replication lag. A user might make a write, then immediately try to read a view that hasn't quite caught up yet. That read your own write's consistency can be tricky.
Okay, lag is a factor.
But on the plus side, it often simplifies concurrency control for writes. A user action often just becomes a single atomic append to the event log, which is much easier to manage than complex locking in a mutable database. It's important to acknowledge, though, that true data deletion, like for GDPR right to be forgotten requests, is surprisingly hard in systems built entirely on immutability. Data copies can live in many layers of the log, making complete erasure difficult.
Ah, the immutability challenge. Okay, we've explored how streams are generated, transmitted, how they relate to databases, but what do you actually do with these continuous flows of data? Our sources seem to break down stream processing into roughly three broad categories.
Yeah, the first category is fairly straightforward. You can take the data in the event and just write it to a database or a cache or a search index,
Yeah.
basically keeping that target system continuously in sync with the source stream.
So like feeding data into other systems.
Exactly. It's the streaming equivalent of how traditional batch jobs produce derived data, but it happens in near real time.
Okay, what's the second category?
The second way streams are used is by pushing events directly to users.
Like alerts.
Yep. Think instant email alerts or real-time dashboard updates. This is crucial for things like fraud detection systems, blocking a credit card, the instant suspicious activity is detected, or maybe manufacturing systems alerting on machine malfunctions right as they happen.
So the human is the end consumer.
Often, yeah, in these critical, time-sensitive cases.
And the third category, you said this is where it gets really powerful.
Right. Third, you can process one or more input streams to produce other output streams. You can build these complex pipelines of processing steps.
Processing streams to create new streams.
Exactly. A piece of code doing this is typically called an operator, or maybe a job. And the crucial difference from traditional batch jobs, again, is that a stream never ends, which means operations like, say, globally sorting the entire data set just don't make sense on an unbounded stream.
Right, you can't sort something that never finishes.
And also, fault tolerance becomes a much trickier problem. These jobs might be running continuously for months or years. Simply restarting from the beginning isn't really an option like it is in batch.
That makes sense. Let's dig into that processing part. One major use case developed back in the 90s, apparently, is complex event processing, or CEP. How does that work?
Yeah, CEP is pretty cool. It's almost like applying regular expressions, but to event streams instead of text.
Regex for streams?
Kind of. You define specific rules to search for patterns across multiple incoming events over time. And when a pattern match is found, the CEP system emits a new, complex event. The queries themselves are stored long-term, and the incoming events continuously flow past them, triggering alerts or actions when patterns match.
Can you give an example?
Sure, maybe spotting a pattern like user logged in from a new device, then immediately tried to transfer a large sum of money. That could be a complex event indicating potential fraud. Systems like Esper or IBM Infosphere streams are known for this.
Okay, that makes sense. And what about stream analytics? How does that differ from CEP?
It's related, but different. While CEP looks for very specific, predefined patterns, Stream Analytics focuses more on aggregations and statistical metrics over many events, often within defined windows of time.
Windows of time,
Like calculating the rate of events per second,
Mm.
or maybe computing rolling averages of sensor readings over the last 5 minutes, things like that. Sometimes, for really massive streams, they even use probabilistic algorithms like Bloom filters or hyperlog to get approximate results very efficiently.
approximate but fast.
Exactly. Popular frameworks you hear about in this space include Apache Storm, Spark Streaming, Apache Flink, and Kafka Streams.
Okay. And connecting back to our earlier discussion about databases as streams, stream processing is also vital for maintaining materialized views, right?
Absolutely. This means constantly updating things like caches, search indexes, or even the drive state in event-sourced applications. You're essentially consuming streams, and maybe CDC streams, maybe event-source streams that conceptually stretch back to the beginning of time, apart from maybe compacted data, to keep these views fresh. This also enables things like search on streams. Imagine a system like Elasticsearch's Percolator feature, where you can store search queries and then continually match incoming documents, like news feeds, against those saved queries in real time.
So you match the data to the query, not the query to the data.
In a sense, yeah. The queries are static, the data flows past.
Now, that begs the question, Both stream processing and things like actor frameworks, maybe used for RPC, involve messages. What's the core difference in their purpose? Are they the same thing?
That's a great distinction to make. They're definitely different. Stream processing is primarily a data management technique. It's focused on building these durable, multi-subscriber, often electric data pipelines for processing flows of data.
Okay, data pipelines.
Actor systems, on the other hand, are typically more about concurrency and managing the distributed execution of individual, often stateful, modules or components within a larger application. They're less about the data flow guarantees and more about coordinating behavior.
Different focus. Got it. The upshot of all this processing, especially analytics, is that when you're dealing with continuous streams, things like the average over the last 5 minutes, the concept of time itself becomes surprisingly nuanced, doesn't it?
It truly does. It's way more complex than you might think initially. In batch processing, you typically use the timestamp that's in the event data itself, what we call event time.
The time it actually happened.
Right, that gives you deterministic, repeatable results because the time you run the batch job, the processing time, is irrelevant to the historical data's meaning. However, many early stream processors actually defaulted to using processing time, the local system clock of the machine doing the work for defining those time windows.
Why would they do that? Sounds wrong.
Well, it's simpler to implement initially, but as our sources clearly show, this approach completely breaks down with any significant processing lag.
Lag from what?
Network queues, maybe the system was down and restarting, garbage collection pauses, or just general processing backlogs. Any delay between the event happening and it being processed throws processing time windows off.
Can you give an example?
Sure, our sources give a great one. Imagine a user makes a web request to server A, then immediately makes another request to server B. Even if A's event happened first, maybe B's event arrives at the message broker or stream processor sooner due to network quirks.
Okay.
If you use processing time to window the data, you'll see event B before event A, completely messing up the actual order of user action.
Inconsistent ordering.
Exactly. The sources use this brilliant Star Wars analogy. Episode 4 came out in 1977, V in 1980, Ashiri Sai in 1983. But then episodes 1, 2, and 3 came out much later, starting in 1999.
Right, the prequels came later.
If you watch the movies in the order they were released, the processing time, the order you process them, is totally inconsistent with their narrative chronology, the event time. Confusing these two times can lead to really bad data in your analytics, like seeing a false spike in request rates on your dashboard right after you redeploy a stream processor, just because it's catching up on a backlog, even if the actual user activity rate was totally steady.
That's a huge problem for accurate real-time analytics. So if you're defining windows, those time periods for aggregation by the correct time, the event time, how do you even know when you've received all the events for a particular window? Like for the window ending at 10:05 a.m., what about straggler events that arrive super late?
That's the million-dollar question in event time processing. You generally have a couple of options for stragglers.
Okay.
You can choose to simply ignore them, drop late events, though it's always wise to monitor how many you're dropping so you know if your results are skewed. Or your system can be designed to publish a correction to the Windows result once those stragglers finally arrive. Maybe issue an updated count or average.
Corrections. Okay. What about trusting the timestamps themselves, especially for mobile devices?
Another huge challenge. Device clocks can be wildly inaccurate, or maybe the app buffered events offline for days before sending them when it got connectivity back.
Right.
To handle unreliable device clocks, our sources suggest a good practice. Log 3 timestamps if possible. 1. When the event occurred, according to the device's potentially wrong clock. 2. When the event was sent to the server, again, device clock. And 3. When the event was actually received by the server, using the server's more reliable clock.
3 timestamps. Why?
By comparing these 3, you can estimate the clock skew and get a much better estimate of the true event time, even if the original device clock was off.
Clever. To explore this further then, once you've hopefully figured out a reliable timestamp, how do you actually choose your window type for doing these aggregations?
Right, you need to define the boundaries.
Yeah.
There are a few common window types used in stream processing.
Okay.
A tumbling window has a fixed length, and they are completely non-overlapping. Thing like perfect 1-minute blocks. 10.03.00 to 10.04.59 is one window, 10.04.00 to 10.04.59 is the next.
Simple blocks. Got it.
Then there's a hopping window. It also has a fixed length, but it overlaps, moving forward by a smaller hop size. This helps smooth out data. For example, you could have a 5-minute window that hops every 1 minute. So you'd calculate results for 10.03 to 10.07, then 10.04 to 10.08, then 10.05 to 10.09, and so on.
Overlapping. Okay, for
Yeah.
smoothing.
Yep. Then a sliding window is a bit different. It contains all events that occur within some specified time interval of each other. For instance, a sliding window might group all events where no two consecutive events are more than, say, 5 minutes apart. The window slides along with the data activity.
More dynamic based on the data itself.
Right. And finally, a session window, which is very common for website analytics. It has no fixed duration at all. It groups together all events for the same user, and the window closes only when there's a defined period of inactivity, like no clicks from that user for 30 minutes.
Grouping by user activity bursts. Makes sense.
Okay, just like in traditional batch processing, joining different data sets is absolutely crucial in streams too. But with continuous data and all these complexities around time and windows, it sounds like it gets even more
That
complex.
definitely does. That begs the question. If new events can appear literally any time on multiple streams, how do you join them reliably? Our sources helpfully distinguish three main types of stream joins.
Okay, what's the first type?
First is a stream join, sometimes called a window join. Here, both inputs are active event streams, and you're essentially searching for related events arriving on both streams within a specific time window.
A classic example is joining a stream of user search events with a stream of user click events, maybe matching them by a session ID to calculate click-through rates. You need a time window because the click might arrive much later or even slightly earlier than the search event it relates to.
And this requires...
This type of join requires the stream processor to maintain a significant amount of state, basically buffering all the relevant events from both streams for the duration of the time window, say the last hour.
Okay, requires keeping state. What's the second type?
Second is a stream table join. This is often called stream enrichment. Here, an active event stream, like user activity, is joined with a more static or slowly changing table, think like a user profile database.
Enriching the event data.
Exactly. You might enrich user activity events with details from their profile, like their location or subscription level. This often involves loading a snapshot of the database table into the stream processor's state and then keeping it continuously up to date by consuming a change data capture (CDC) stream from that database.
Using CDC to keep the lookup table fresh. Clever. And the third type?
Third is a table-table join. This sounds a bit weird for streams, but it's really about materialized view maintenance based on changes to underlying tables. Here, both inputs are effectively database changelogs, CDC streams.
Both are change streams. Example.
A great example given is maintaining a Twitter home timeline cache. Changes to the tweets table, new tweets, deletes, and changes to the follow graph table, user A follows B, are both processed as streams. The join logic figures out which users' timelines need to be updated based on these incoming changes. It's essentially like maintaining a materialized view of a complex SQL join, but updated continuously in real time.
Wow, that's quite sophisticated. Bringing this all together then, the implication seems to be that all these join types require the stream processor to maintain some kind of state and query it constantly. But I see a big challenge you mentioned earlier, time dependence. If events on different streams happen around the same time, in what order are they processed by the join operator? That sounds like it could make the join results non-deterministic, right?
You hit on a critical point. It absolutely can. The exact order in which events from different input streams are processed relative to each other can affect the join output, especially if you're joining based on time windows. Zooming out a bit, this challenge is actually quite similar to dealing with slowly changing dimensions, SCDs, in traditional data warehouses.
How do they handle it?
One common solution, both in SCDs and stream joins, is to use unique identifiers for different versions of records over time. Effectively, you give each change or state snapshot its own identity. However, a significant implication of this is that you often can't use long compaction on the input streams for these time-sensitive joins,
Why not?
because you might need all the historical versions of a record, like all historical addresses for a customer, to perform accurate joins based on the event time of the other stream. If you compact the log, you lose that history, so it can impact storage significantly.
Trade-offs, always trade-offs. Okay, finally, let's talk about reliability. This seems crucial for systems processing potentially critical data endlessly. In batch processing, if a task fails, you generally just restart it, right? And its partial output gets discarded. This kind of gives the illusion of exactly once semantics, even if some records might get processed multiple times internally during retries. But how on earth do you achieve something like that with an infinite stream that's constantly producing output? You can't just restart the whole infinite stream.
You're right, waiting for an infinite stream to finish before committing output just isn't an option. Stream processing needs different fault tolerance mechanisms. One common solution is microbatching.
Microbatching.
Yeah, frameworks like Spark Streaming use this. They break the continuous stream into tiny, discrete blocks, say batches of 1 second's worth of data, and then treat each microbatch like a miniature deterministic batch job. If a microbatch fails, it can be retried.
Okay, treating it like tiny batches, what's another approach?
Another method, common in frameworks like Apache Flink, uses distributed snapshots or periodic checkpointing. The stream operators periodically save their internal state to durable storage. So if an operator crashes, it can simply restart from its most recent checkpoint, reset its input streams to that point, and discard any output generated since that checkpoint.
Checkpoints. Okay. But do these methods guarantee exactly once?
Well, they typically provide exactly once semantics within the stream processing framework itself, meaning the internal state updates will be consistent with the processed inputs. However, there's a catch. If the output of the stream processor leaves the framework, say, it writes to an external database, sends an email, or calls an external API a retry after a failure, can cause those external side effects to happen twice.
Ah, the external side effect problem. That's a critical distinction. So to achieve true exactly once processing, including those external side effects, you need something more robust, right?
Mm.
How do specialized stream processing systems handle this atomic commit problem we've talked about before, but efficiently enough for high throughput streams?
This is where the real ingenuity in modern stream systems comes in. Specialized systems like Google Cloud Dataflow or platforms like VoltDB, which combine streaming and transactions, and increasingly capabilities within Apache Kafka itself, implement variations of the atomic commit protocol, but optimized for stream processing workloads.
How do they manage that?
These systems typically manage both the stream processing state changes and the output messaging or database writes together, often within their own frameworks. They ensure that all outputs resulting from processing a particular chunk of the stream happen atomically, meaning either they all succeed and get committed together or they all fail and get rolled back, preventing those dreaded duplicate external side effects upon retry.
Integrated atomic commit for streams. Got it. And what if a system can't do that full atomic commit? Is there another strategy for reliability, maybe something the application developer can do?
Yes, absolutely. The other main approach is to rely on idempotence in the downstream systems or operations.
Idempotence, meaning you can run the operation multiple times with the same result.
Exactly. An idempotent operation has the same effect no matter how many times you perform it with the same input. For instance, setting a key value pair to a specific value is idempotent. Doing it twice is the same as doing it once. Incrementing a counter, however, is clearly not idempotent. Doing it twice doubles the increment.
Right. So how does that help with stream processing failures?
Well, if the operation that produces the external side effect is idempotent, then it doesn't matter if the stream processor retries it after a failure. The end result will still be correct. You can often make non-idempotent operations effectively idempotent by adding extra metadata. For example, when writing an update to a database, you could include the unique offset of the Kafka message that triggered the update. The database update logic can then check if it's already processed that specific offset and skip the duplicate update if it has.
Using unique IDs from the stream to deduplicate downstream. Clever.
Yeah, but it requires careful handling. You need deterministic processing in your stream job. You often need to replay the exact same messages in the same order upon retry, and you have to handle potential concurrent updates carefully.
Okay. And what about the state itself? All those aggregations for windowing or the state needed for joins, that state has to survive failures too, right?
Absolutely critical. For any state a stream process needs to maintain, that state must be recoverable after a failure. There are a few ways to handle this. You could keep the state in a remote replicated data store, like an external database or key value store.
But that could be slow. Network hops for every state update.
It can be, yeah. The alternative is to keep the state local to the processing node for speed, but then periodically replicate it or back it up somehow. Frameworks like Flink snapshot their local operator state to distributed storage as part of their checkpointing. Systems like Kafka Streams or Soundza actually replicate state changes to special log-compacted Kafka topics using Kafka itself as the durable replicated state store. It's very much like using change data capture for the stream processor's internal state.
Using the log for state too. It all comes back to the log.
It often does. Stepping back, sometimes if the state needed is relatively small or only covers a recent time window, it might even be feasible to just rebuild the state entirely by replaying the necessary input events from the source stream after a failure.
Rebuild from scratch on restart.
Yeah. The best choice, remote state, local replicated state, or rebuilding from input, really depends on the specific performance needs, the size of the state, the recovery time objectives, and the underlying infrastructure. It really shows there's truly no one-size-fits-all solution for state management and reliability and stream processing.
So what's the big takeaway from all this then? We've taken a really deep dive into stream processing, from its fundamental differences with traditional batch processing to the intricate ways data flows through message brokers and these powerful log-based systems.
Yeah, and we've seen how databases themselves can actually be viewed as just streams of changes. That idea enables incredibly powerful real-time data synchronization and insights across really complex systems.
We've explored how these continuous data flows get put to work in everything from instant fraud detection to real-time web analytics, and maybe surprisingly, the complexities introduced by the concept of time itself.
Especially that crucial, tricky distinction between event time and processing time. And perhaps most importantly, how modern systems are tackling reliability in this world of endless data, moving ever closer to that elusive exactly once processing promise, even when dealing with those tricky external side effects.
What stands out most to you from our discussion? Maybe it's that subtle dance between event time and processing time, or the really clever ways logs are being used not just for messaging, but for durable, replayable data storage, fundamentally transforming how we even define what a database is.
For me, it's probably that log-centric view,
Yeah.
the idea that the log holds the truth.
Yeah, me too. So let me leave you, our listener, with this provocative thought. If the truth is the log, as Pat Helen said, an all mutable state we see in databases is merely a derived cached view, how might thinking about every data interaction, every change as an immutable event fundamentally alter how we design all our digital systems, from the smallest mobile app to the largest enterprise platform? What new opportunities does this unlock for things like true, indisputable auditability, for genuine real-time understanding of complex systems, and maybe even for undoing digital mistakes with the kind of grace and clarity you see in an accountant's ledger? Something to think about.